Have you ever just stopped and wondered how your computer is so fast? How it can find one specific photo among thousands, like, instantly? Well, the secret isn't just about a faster processor. It's actually a really simple, incredibly elegant idea about how computers search. Let's get into it. We all get this, right? It's instinct. If you're looking for someone named Smith, you're not going to start at A and read every single name. No way. You open the book somewhere in the middle, see you're at the M's, and in that split second, you know the entire first half of the book is completely useless to you. That one move, that decision to just ignore a giant pile of data, that's the core secret we're going to unpack. And this is the fundamental shift in thinking we're talking about. A search isn't just some boring procedure. It's a mindset. The difference between a slow, clunky search and a lightning-fast one is all about the strategy. It's about the questions you ask yourself along the way. So to really appreciate the computer's genius approach, we first have to look at our own default method. Let's call it the human way. It's the most straightforward, intuitive approach you can possibly imagine. This is linear search, and it is exactly what it sounds like. You've got a list, and you start right at the beginning. You pick up item number 1 and ask, is this it? No? Okay, on to the next one. How about this one? You just keep chugging along down the line until you either find the thing you're looking for or you run out of stuff to check. Now, there's a reason this method is so intuitive. It actually has some great things going for it. You don't need to organize your data at all. It can be a complete mess. Doesn't matter. You just grab the list and go. There's zero prep work, which makes it super, super simple. In computer science, we have this concept called time complexity. I know, it sounds a little intimidating, but it's really just a way of asking, how much slower does this get as my list gets bigger? In the absolute best case scenario, you get really lucky, and the item you want is the very first one you check. Boom, you're done. But in the worst case, it's the very last one, or maybe it's not even in the list at all, and you had to check every single item just to be sure. And here's the key takeaway from all that. There's a direct one-to-one relationship here. If you double the amount of data, you're going to double the search time. The effort grows in a perfectly straight line, or linearly, right along with the size of your list. For a small number of things, this is totally fine. If you're looking for a specific t-shirt in a drawer with 10 shirts in it, checking them one by one is no big deal at all. It's fast enough. But what happens when you're Spotify and you need to find one song out of 10 million? Suddenly, that one-by-one approach feels incredibly slow and painful, right? The problem has just gotten way too big for our simple, human-friendly method. And for the kinds of data sets that run our modern world, we're talking billions of web pages, trillions of database entries. This linear way of thinking isn't just slow, it is computationally impossible. It would take years, maybe even lifetimes, to find anything. This problem created an absolute need for a smarter, better strategy. And that brings us to the computer's way. And this isn't just some slightly faster method. Oh no. This is a completely different philosophy of searching. And it's just brilliantly elegant. Okay, so before we can even start, there is one critical rule, one non-negotiable condition. The data must be sorted. Remember our phone book? It only works because the names are in alphabetical order. This is the trade-off. It's the price of admission. You have to do the work to organize your data first if you want to unlock that incredible speed. This is called binary search, and it's a perfect example of a powerful strategy called divide and conquer. Instead of starting at the beginning, you jump right into the middle of the list. You check that one item. If it's not a match, you just ask a simple question. Is the thing I'm looking for smaller or larger than this middle item? And based on that answer, you just throw away the entire half of the list where your target could never be. Then you just do the whole thing over again on the smaller piece that's left. And this is the source of its power. You're not just eliminating one item at a time. With every single check, you are eliminating half of the entire problem. The search space just collapses exponentially. So let's go back to that big number. Imagine a sorted list with 1 million items. A linear search, in the worst case, could take 1 million steps. But with binary search, it takes about 20 comparisons. No, that is not a typo, 20. 1 million items becomes 500,000, then 250,000, then 125,000, and in about 20 steps, you've pinpointed the exact item. That's the difference between an impossible task and an instantaneous one. This right here is why computers feel like magic. So we have these two approaches. One feels so natural to us, and the other one feels almost alien in just how efficient it is.
They really represent two fundamentally different ways of thinking about how to solve a problem.
And this slide really gets to the philosophical difference between them. Linear search is basically just a process of hopeful, repetitive checking. It just keeps asking, is this the one? How about this one? Binary search, on the other hand, is a process of strategic elimination. It's not really trying to find the right answer. It's focused on figuring out which answers are definitely wrong so it can get rid of them as fast as possible. Let's break it down side by side. Data requirement, linear search works on anything. Binary search needs it to be sorted. Strategy, linear is sequential, one by one. Binary is that powerful divide and conquer idea. Then you have time complexity, and we use this shorthand called big O notation. Linear search is O of n, meaning the time grows with n, the number of items. Binary search is O of log n, which is the math behind that amazing scaling we saw. And it all boils down to the thinking style, the intuitive human way versus the powerful algorithmic way. Now, it's really easy to look at this and think, okay, binary search is always the answer. But in engineering and computer science, everything is about trade-offs. There's a price to pay for all that incredible speed. These are some of the classic pitfalls. The most obvious one is trying to use binary search on a list that isn't sorted. It'll just give you complete garbage. When you're coding it, there are also some tricky details, like getting the boundaries right so you don't miss an answer or get stuck in an infinite loop. But the most subtle mistake is just assuming that because binary search is faster, it's always the better choice. And here's why that is. What about the cost of sorting the data in the first place? That takes time and effort. If you have a huge, messy list and you only need to find one thing, just one time, it might actually be faster to do a simple linear search than to spend all that time sorting the entire list first. The total time, that's preparation plus the actual search, is what really matters. This brings us to the final core lesson that these algorithms teach us, and it's a lesson that goes way beyond just writing code. It's really a lesson in problem solving itself. This is the ultimate takeaway. True efficiency, whether we're talking about computers or our own lives, doesn't come from just grinding harder, from trying to get through every single possibility with more force. It comes from having a smarter strategy. It's about asking the right questions that let you throw away entire categories of wrong answers. Computer speed isn't magic. It's just the art of intelligently ignoring what doesn't matter so you can find what does, almost instantly.